So chapter 3 was called A World of Particles, and it was where we were first introduced to the atom and the subatomic particles that make up every single atom in the universe. We first started with an overview of sort of the history and the development of the atomic model. And while you don't have to, you're not going to be held responsible for knowing which model belongs to which person, you should have an understanding of what a scientific model is. Remember, it's a simplistic representation of something more complex. We use models in all aspects of science. In meteorology, we use them in biology, but in chemistry, the most popular model that we use is the model of the atom. It's giving us a visual for the atoms that we can't see. And the overall understanding and the conceptual piece that's important here is how the model and the historical development of the atomic model is progressive and that it continues to evolve over time. And if we look at the models here, the way in which they evolve to become more complex than they were before. So Dalton, if we look at where we first start, Dalton had the most simplistic model of all, which was the solid sphere model. We then had J.J. Thomson, who used the cathode ray tube to discover electrons, which was the first subatomic particle that was discovered. He came up with the plum pudding model. We had Rutherford do the gold foil experiment to discover the nucleus, that dense small positive center of the atom. Bohr used experimental evidence to say that electrons were orbiting the nucleus in these different levels, that they can move between the levels. And then Schrödinger was one of among many scientists who developed the model that we currently have, the most accurate model, which is the quantum model or the wave mechanical model. And it only slightly differs from the planetary model. The only difference is that the electrons are not going in these distinct or finite orbits. We can't actually say where the electrons are on the outside of the nucleus, like, away from the nucleus. We have to talk about their location as a region of space where they will probably be located, and we define that as an orbital. So an orbit's a definite path, where an orbital is a region of probability where an electron is most likely to be found. The three subatomic particles that make up every single atom in the universe are protons, neutrons, and electrons. You should be familiar with the symbol, their charge, their mass in atomic mass units, and their location with respect to each other in the atom and to the nucleus. Although the quantum model is our most accurate and most current, the model that we use commonly in chemistry and the one we used throughout the year looks more like the Bohr model or the planetary model. We call it the simple atomic model, really because it's just easier for us to draw, and it gives us all the information we need to know. So the protons and neutrons are still together in the nucleus. The electrons are still on different levels. The only thing is they're not orbiting. So really the quantum model says these two electrons here, we wouldn't be able to say they're exactly in that spot. There are two electrons on that first energy level. We just don't know exactly where they are in that energy level. But that's okay. We don't really have to worry about that for the stuff that we looked at this year. We can identify what element this is by counting up the number of protons. There are 6 protons here, and that corresponds to the atomic number, which then we can reference on the periodic table. It's the biggest numbers on there. Atomic number 6 is carbon, so this atom is an element of carbon. There are 6 neutrons here in the nucleus, which tells me that the mass of the atom is 12 atomic mass units. Each proton has a mass of 1. Each neutron has a mass of 1. So 6 AMU plus 6 AMU gets me 12. The electrons have virtually no mass, so we don't even count them up in the mass of an atom. Now this is one very specific isotope of carbon, and the symbol for that isotope is here. Here is an outline of how we would write an isotopic notation or an isotope symbol using the symbol of the element, the atomic number, and the mass number. Recall that isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons, so therefore their masses are different. There are a few different ways in which we can show the symbol of a specific isotope, and those are all listed here. This way is really what we would call the isotope. So we might write it as any one of these ways, but the way we would read the name of an isotope is the name of the element and its mass. So carbon 14 or carbon 13 would be the name of the isotope, no matter which one of those symbols we decided to use to represent it. If we're given the symbol of an isotope, we can figure out the number of neutrons in that isotope, because the mass number, like we calculated up here, we get from adding the protons and neutrons together. So if I know the protons and neutrons together and I have the atomic number, which is the protons, I can subtract out the atomic number from the mass number to figure out how many neutrons there are. So you can see in silicon 28 there's 14 neutrons, in silicon 29 there's 15, in silicon 30 there's 16. The number of electrons are the same because, remember, by definition, atoms are neutral. So the number of protons and electrons have to be equal. One other quick note is that this way of representing isotopes is actually really common. It looks like it's missing information, but remember, the atomic number is not really needed in the symbol. We have the symbol of the element, which is C, and I can go to the periodic table and see from there that the atomic number is 6. So we don't actually have to write it in. And if you don't see it there, you know how to reference the periodic table to figure out what the atomic number is. On the periodic table, in terms of the information that's there, we have the element symbol, which is in red here, the atomic number, which is in green, that's the number of protons, and then we have this number as a decimal, which is called the average atomic mass. So we have the atomic number here, we have the element symbol, and then we have the average atomic mass. Now the average atomic mass is a decimal because it's an average of the masses of the naturally occurring isotopes of a given element. So carbon, all the carbon that exists in the universe, comes in one of 3 types. Carbon with 6 neutrons, carbon with 7 neutrons, carbon with 8 neutrons. That's carbon 12, 13, and 14 respectively. So I cannot say that carbon has just one mass because it can actually be one of 3 different masses. But if we pick up a lump of charcoal, let's say, that's all carbon, the distribution of carbon atoms or carbon isotopes in that charcoal, it follows a very specific ratio. We call that percent abundance. So the percent abundance of carbon 12 to carbon 13 to carbon 14 is going to allow us to figure out what that average atomic mass is. So average atomic mass is the weighted average of all the naturally occurring isotopes of an element, and it's going to be closer to the isotope that is present in greater abundance. So an example here, the 2 most common isotopes of carbon are carbon 12 and carbon 13. Carbon 12 exists as 99% abundance and carbon 13 exists as 1% abundance. What that means is that in the universe, 99% of all carbon atoms have a mass of 12 AMU and 1% have a mass of 13 AMU. Said another way, if we assume that we have a sample of 100 carbon atoms, 99 of those atoms are going to be carbon 12 with a mass of 12 AMU, and one of those is going to be carbon 13 with a mass of 13. So how do you describe the average mass? Well, we take a weighted average. We take the mass of one isotope and we multiply it. If we assume that there's 100 atoms, we multiply it by how many of those atoms have that mass. And in this sample, 99 would have a mass of 12 AMU. And we add it to the other mass, 13 AMU, which one atom would have a mass of, and then we divide it by how many atoms we assumed we had in the sample, which is 100. And if we do that, we get somewhere around 12.0 in some decimals AMU. What this tells us is that the majority of carbon atoms have a mass of 12 AMU, and that's reflected in this average atomic mass here. It's closer to 12 because carbon 12 is more abundant in nature. Here's another example we can look at here with magnesium. Magnesium has an average atomic mass of 24.31 AMU. The isotopes that exist for magnesium are magnesium 24, 25, and 26. So even without the percent abundance listed here, we could predict that magnesium 24 is the most abundant because the average atomic mass, or the weighted average, is closer to that value. And again, the way we would calculate that, assume we have 100 atoms. Magnesium with a mass of 24, 78.99 of those atoms would have that mass. 10 atoms would have a mass of 25, and 11.01 atoms would have a mass of 26. We divide that by 100 atoms because that's how many atoms total we assumed in our sample, and then we get 24.31 as our average atomic mass. We can answer lots of interesting questions, like take silver, for example. I gave you the box, it's periodic table element box here. Predict the two most abundant isotopes of silver. Just based on this atomic mass, if we know we're averaging them together, we would predict that silver 107 and silver 108 would be the two most abundant isotopes of silver. The one that is most abundant is going to be most likely silver 108, as the average atomic mass is closer to it. So it's pulling the weight of that mass closer to that value. How many protons, neutrons, and electrons would each of those isotopes contain? Well, the periodic table comes in handy for helping me figure out the protons and electrons, because as long as it's a neutral atom, then the number of protons and electrons are going to be the same. So that would be 47 protons and 47 electrons in each one. Now, in terms of the neutrons, we have to take the mass and subtract out the atomic number. So 107 minus 47 gets us 60 neutrons in this isotope of silver 107. And in silver 108, 108 minus 47 gets us 61 neutrons. The last part of this chapter had us looking at nuclear chemistry, and we started off by talking about and looking at nuclear stability. Now, nuclear chemistry is all about the chemistry going on in the nucleus of the atom. Nuclear stability has to do with the ratio of protons to neutrons, and every isotope has a specific ratio that makes it stable. If the ratio of protons to neutrons is not stable or unstable, then that nucleus is going to decay to become more stable. I gave you a snippet here of the isotope chart that we used extensively in this chapter. Remember, it plots the number of protons on the x-axis and neutrons on the y. And this allowed us to look at, first of all, for a given element like helium, how many isotopes exist. Each box represented an isotope that existed naturally. And then they were color-coded to say which is the most abundant isotope, the ones in black, which were just other isotopes, the one on this diagram red, and which isotopes were radioactive, which are the ones in white here. This led us into a discussion on the difference between natural versus stable. Just because we're saying an isotope is natural does not mean it's stable. Natural means it's found in nature, meaning I can go out and find it somewhere. It's not man-made in the lab. Stable means that it's not radioactive or undergoing decay, meaning that it's satisfied by its ratio of protons to neutrons that it currently has. Elements after number 82 have no stable isotopes, so all of the ones in yellow here, technetium is an exception in many ways. And then elements after 92 are all man-made, so that would be from neptunium on. So again, what we're saying here is elements after 82 have no stable isotopes. All the isotopes that exist for them are going to undergo decay. Where elements after 92, although all of their isotopes are also unstable, those are all man-made in the lab. So like uranium, palladium, thorium, those can be found in nature, but neptunium, plutonium, americium cannot. They were all found in the lab. They're all made in the lab, I should say. Then we looked at in what ways do these isotopes decay. If they are unstable, how are they going to decay? So this led us into a discussion on nuclear reactions, which are the ways in which unstable isotopes will decay. And there were three main decay modes we looked at: alpha, beta, and gamma. I gave you a visual for each here, brief definition of what's going on. We looked at the penetrating power of each, right? The alpha particles are big and bulky, so they don't make it through most things. Beta are smaller, so they could make it through some more substances, but are stopped by something like aluminum foil. Where gamma radiation is not a particle, it's really just energy. So it makes it through most things. The only thing that will stop it or really dissipate its effect is lead, because of how dense lead is. This table summarizes the changes that we see, what a generic equation would look like. Alpha decay is essentially a helium nucleus that's being broken off of the nucleus that's changing. So it's 2 protons and 2 neutrons that are leaving the unstable nucleus. The atomic number decreases by 2, the atomic mass decreases by 4. Beta decay is where we have a neutron turning into a proton in the nucleus, so the atomic number increases by 1, but at the same time an electron is generated also, and that electron comes flying out, really high energy. That's what we call the beta particle. And then gamma radiation is just energy, and it's really accompanied with other decays. So whenever something's undergoing alpha decay or beta decay, we'll get gamma radiation to occur as well. Gamma decay does not change the identity of the nucleus because it's not changing the number of protons and neutrons like alpha decay or beta decay is. Here we're going to work through some examples of alpha and beta decay just to review that you can write nuclear equations and look at what new elements or what new isotopes are forming after a given decay. So let's take a look at this first example. I have tungsten 184 undergoing alpha decay, and I could see its alpha decay because I see an alpha particle that's being emitted. It's on the right-hand side of the arrow. And to figure out what my new isotope is going to be, because an alpha particle is 2 protons and 2 neutrons, the atomic number is going to decrease by 2. So my new atomic number is 72, and my atomic mass is going to decrease by 4 units. So I get 180. And then to figure out what the symbol is, we can reference the periodic table. 72 is hafnium, HF. So that would complete that alpha decay. For this beta decay of carbon-14, remember in beta decay, a neutron is turning into a proton in addition to the beta particle. So the atomic number is going to increase by 1. The mass number is going to stay the same because neutron turning into a proton, 1 AMU lost, 1 AMU gained. So we have 14 and 7 here, and then we look on the periodic table. This is nitrogen. We can do a quick check by making sure the numbers on the top add up to the numbers on the bottom. I'm going to ask you to pause the video, try the other examples, and then you can unpause and check your work. So here are the answers to these sample problems. The missing substance can be the new isotope. The missing substance could be the particle that's being emitted, the alpha or beta particle, or it could be the starting isotope. Remember, we used vocabulary like the parent isotope and the daughter isotope. The parent is what we start with. The daughter isotope is what's formed. We could write out the equation just given the parent isotope and what decay mode it's going to undergo. So you should be familiar with, those types of problems. The last thing that we looked at in this chapter was nuclear fission and fusion. Fission and fusion, we should know the differences between those two types of nuclear reactions. Fission is where we have a nucleus that's splitting into 2 lighter, smaller nuclei, where fusion is where we have 2 lighter nuclei fusing or coming together to form 1 heavier nucleus. Fission reactions we commonly see in nuclear power plants that power many cities and states across the US. Fusion we only really see in stars like our sun. Fusion requires much, much more energy to occur, though we get a lot more energy out of a fusion reaction than we do fission. Both of these in general give out a lot of energy, much more than any chemical reaction. So as far as nuclear reactions go, we get way more energy from them. But fission we commonly see here on Earth in power plants. Fusion we only see in stars like the sun. And here are a couple of other example problems that we can look at. These are not alpha or beta decay, but these are fission and fusion reactions. So here I have palladium-231, and I see that iridium-192 is one of the isotopes that's formed. If we follow the same rules here, if I'm missing one thing, and there's 77 protons there, and I'm starting with 91 protons, then if we do a quick subtraction, we can do 91 minus 77, get 14. And then same thing with the mass, 231 minus 192 to get 39. And then we look in the periodic table, and element number 14 is silicon. This is not alpha or beta decay because we're not producing an alpha or beta particle. What this is saying is that palladium-231 is splitting into iridium-192 and silicon-39. That is an example of a fission reaction, the one heavier palladium isotope splitting into two lighter nuclei. On the right-hand side here, we have a fusion reaction. I have a helium nucleus and a hydrogen nucleus coming together to form one nuclei. 2 protons and 1 proton give us 3. 4 plus 2 mass units give us 6. The third element on the table is lithium, so this is a fusion reaction that's forming lithium-6. So again, you can pause the video, try the 2 additional reactions, and then unpause to check your work. So you can check your work there. We get bromine-103 is the additional isotope formed in the fission of plutonium-244, and neon-21 formed from the fusion of beryllium and carbon. The very last thing we talked about to wrap this all up and tie it back to our theme of alchemy is, can we make gold from nuclear reactions? We saw in chapter 2 that we were unable to do so via chemical reaction because atoms in a chemical reaction just unbond, rearrange, and rebond with other things. But in a nuclear reaction, it was the first time we saw that we can actually change one element into another. So can we make gold here on Earth via nuclear reactions? Alpha decay, we said in class, was a no-go, because the isotope that would have to undergo alpha decay to turn into gold does not exist in nature. Same thing with beta decay. The isotope that would have to undergo beta decay to turn into gold, non-existent in nature. Fission, we could potentially, but the problem is we can't predict when a nucleus splits or fizzes. We can't predict what 2 nuclei we are going to get, or 3 or 4, however many it's going to split into. So even if we do form gold, it's not very efficient. We wouldn't get a lot, and it's dangerous to run fission reactions, right? In nuclear reactors, they are encased in thick walls of concrete to prevent any radiation from getting out to civilization. So our last hope was fusion, and fusion was possible to make gold because we can take 2 elements, when we add their protons and neutrons together, could give us an isotope of gold. The problem is we can't do this on Earth because fusion reactions take way too much energy, heat, temperature, pressure to occur on Earth. That's why they only occur in outer space, in the stars, and like in our sun. So yes, the gold that we have here on Earth was created by fusion, but fusion reactions from the Big Bang that created the universe, and right now there's other gold being made in stars out in our universe somewhere, but in terms of the gold that's here on Earth, was formed when the Earth was created millions of years ago, and it's just been recycled over and over, right? Going back to the idea of the conservation of mass. The one last thing that we looked at was in terms of fusion reactions that happen in stars. A star can take 2 hydrogen isotopes and fuse them to make helium, and then take another hydrogen to make lithium, and another one to make beryllium, and it sort of works its way across the periodic table, fusing elements together to create beryllium, then boron, then carbon, then nitrogen. And stars will do that all the way up until iron. And once stars start to produce iron, it's not energetically favorable for them to produce any elements heavier than iron. So what happens is the star implodes, and that's when we get a supernova. And in the process of the star exploding, there's enough heat and pressure to fuse basically the rest of the periodic table, and that star, upon undergoing a supernova, vomits the rest of the elements in the periodic table across the galaxy into the universe. So that's how the elements were created. So in short, it's sort of yes or no, yes and no for fusion. Yes, that is how gold was formed, the gold we have here on Earth, but it cannot be done on Earth. We cannot run fusion reactions here on Earth. So that brings us to the end of Chapter 3, A World of Particles.